Today we have Dr. Marziya Hasan here with us who received her Ph.D. from Texas A&M and is currently working at Shape Memory Polymers, or is it just Shape Memory? Um,
It's Shape Memory Medical.
Shape Memory Medical, where she's working on polyurethane foams for embolic occlusion medical devices. Um, yeah, so thank you all for joining. We have really exciting talk. We're listening to today. And if it's your first time at our webinar series, we really appreciate you coming. This is our medical plastics division uh, monthly or bi-monthly happy hour webinar series, where we ask authorities in the medical plastics space to present on their work and um, help us broaden our horizons around medical plastics. And so we will have about a 25-minute to 30-minute talk by Dr. Hasan, and then we will move into the Q&A session. If you have any questions, please put them in the chat or save them till the end, and we will address them accordingly after. And then once we're done with the Q&A, we'll be all picking up a glass and sharing a happy hour drink and a little networking session. My name is Dr. William Morris. I got my PhD from Colorado State University. Now I am a board member on the Medical Plastics Division, helping out Len Zuba, help in the Technical Programming Committee get the Happy Hour webinar series going again. We took a little hiatus during conference season for our MD&M West and Midwest technical programming, as well as our Antech conference. And now we'll be picking up the happy hour series again in next year's technical talks. So without further ado, Dr. Marziya Hasan.
All right, thanks, Will, and thank you everyone for joining me today. I'm excited to talk to you guys about my work, and just a heads up, this is not something that only I've worked on. Um, this company has been around for several years, and actually, the work that I'm going to be talking about today is a collective effort. Um, so Shape Memory Medical, we are located in the Santa Clara, San Jose area in California. We have licenses with Lawrence Livermore National Lab and Texas A&M University. And that's because this research initially started at Lawrence Livermore by Duncan Maitland, who then took this research over to Texas A&M as a faculty member and kind of grew out these projects and the shape memory polymer technology throughout his tenure at Texas A&M University. And that's kind of where I joined as well. Present day, however, we have different sections that we're interested in pursuing are SMP materials specific to medical applications. But today, I'm specifically going to be talking to you about the embolization division. We have done some work in structural heart in the lung biopsy space, and then we also provide OEM services to other companies who are interested in using our materials, as well as like some drug delivery grants that we have worked on as part of an academic research environment. But again, today's topic will be focused specifically on the embolic area. So as part of the timeline, as I mentioned, this research started at Texas A&M University in the Biomedical Engineering lab under Duncan Maitland. I joined his lab in 2013. And I worked on the actual shape memory polymer foam that we're going to be talking about today, that is in our devices that are FDA approved. In 2016, Shape Memory Medical became a more corporate entity, and we actually got a new CEO, and he moved everybody out to California. So a lot of the graduate students from Texas A&M, including myself, we moved out to California to work for this company. And now, present day, we're at around 50 54 people. We started with 6 people. So we've definitely grown over the years. And it's a very good group of people to be working with, for me at least. Um, so our product portfolio, we currently have 2 FDA approved devices, which are just iterations of themselves. Our very first impede embolization plug is a shape memory polymer foam component with a marker band and an anchor coil, and I'll kind of go into what that does or what the point of all these different components is. Our second product, which is just an iteration off of this first plug, it's the same design minus the anchor coil. So this is more of a plug that can be used for sac filling or larger volume filling where you don't really need an anchor coil, whereas the anchor coil is specifically designed for blocking blood flow in various vessels. We also have a third product, the Impede FX Rapid Fill. I'll be talking briefly about that today as well. This is currently in a clinical trial, so we do not have any products available on the market for the rapid fill device. As far as indications go for our devices, we can be used anywhere in the peripheral region, and primarily our plugs are used to cause blood to hinder blood flow or to block blood flow in various vasculature, whether it's something as simple as varicocele veins or a little bit more complicated like the pelvic congestion syndrome. We're also able to be used in aneurysms and EVAR procedures. That's something I'll specifically go over today. And the shape memory polymer component is actually very advantageous for use for hemorrhages to block or to treat hemorrhages. And we can also use our devices to block blood flow that's leading into tumors. So in some regard, it can also be used for tumor therapy. So these are just examples of where our plugs have been used in actual clinical cases. These images were provided by various doctors who have used our devices in their patients. So on the left, we have the inferior mesenteric artery, where we have used the Impede plug with the anchor coil, along with the Impede FX to just provide extra volume, extra space filling volume. Then on the right, this is a treatment of an ovarian vein. This is a diseased vein. So what they did was they end capped a bunch of the Impede FX plugs with and the Impede plug with the anchor coil. And again, the anchor coil is there so that the device does not float downstream while the foam is expanding. So our key technology is our devices being self-expanding. So we have a critical component, which is a shape memory polymer. It's a porous foam that can transition between 2 different shapes. We can program this material into a small geometry that is then that can then be deployed through a catheter. So from a medical device perspective, from our specific device perspective, we are able to take our shape memory polymer plug and crimp it to a small cylindrical rod geometry, which it can then be deployed really anywhere in the body using a catheter. Once our devices have exited the catheter and are in the vessel space, the foam component will slowly expand when it contacts blood, and it will cause embolization in whatever area that it's been deployed in. And the way the embolization aspect of this device works is we have an extremely porous material where blood will make its way through the material, through the foam component, and it'll end up stagnating within the pores of the foam. That stagnation triggers the clotting cascade. And that's where we end up seeing the clot that forms to block the blood flow in the rest of the vasculature. And over time, what we have observed is that there is this dense connective tissue that eventually forms around the device. And I'll again go more into detail about this. Our foam component is biodegradable. So over time, we end up replacing our foam entirely with the body's native tissue. Thus, by treating the area effectively and without future treatments that are required. So some of the key properties of our devices is we obviously have the shape memory effect that I talked about. This also, because this foam is extremely porous, and we are using a very low density polyurethane composition for this, there is pretty much no radial force on the vasculature. And the shape memory aspect of the device also allows us to deploy this device into various anatomies using a catheter where it self-expands when it's deployed. The porous structure of the foam is what actually causes clot formation. There's nothing inherent to the material itself that promotes clot formation. It's simply the morphology of the foam, the morphology of the device is what's it's becoming a hemostatic support. And because of these porous materials, as the blood is getting pooled into the various foam cells, there's clot that's being formed, and eventually that results in stable tissue ingrowth. Another thing is that our material is bioabsorbable. That just means that it'll degrade over time, and we have done some work to show that the byproducts from this degradation are non-toxic. Our material is also radiolucent, meaning that it is not visible under X-ray, and that's why we have the marker bands that I showed you guys in some of the previous slides. The marker band is the actual radiopaque component of the device, so that when the physicians are deploying these devices in the body, they know exactly where they are. The foam itself, however, is not radiopaque, but this is beneficial for us because it lets us image the surrounding anatomy without a lot of artifacts. And then lastly, because our foam is bioabsorbable, because it supports good tissue ingrowth, what we've seen over time is that as the material is degrading, that area where the foam was deployed is starting to shrink. And also we've observed that there's not a lot of chronic inflammation. Actually, all the inflammation kind of goes away around the 3-month mark. Here we're just comparing our device to some of our competitors in the market. So on the very left, we have the Impede embolization plug. The yellow pieces are the foam, and the pink represents the surrounding tissue, the collagen that's kind of that's being deposited throughout the vessel. In the middle, we have the Cook Nestor platinum coils. And what you'll observe is that there's a lot of this white space that's showing up, and that's because of recanalization that's taken place because the resulting clot from these platinum coils was not quite as stable. So when the clot is not stable, a lot of the times there is aneurysm recanalization that can take place, and these images specifically are referring to an aneurysm. And then on the very right, we have the Amplatzer plug. Here, this is just a mesh, a nitinol mesh plug where same concept, blood will pool and hopefully form a clot. But from this observed white space, we can see that there is a very large unstable clot because there's a big area where recanalization has taken place. So overall, compared to all of some of our current competitors in the market, we have the best outcomes in regard to tissue ingrowth and the stability of the clot. So now I'm going to talk a little bit more about our AAA SHAPE study, and this is specifically regarding the rapid fill device that is not approved currently in the US. So this is just our disclaimer that these devices are not approved. They're for investigational use only. And further, we're in a clinical trial right now for these specific devices for this specific indication, which is to treat prophylactic abdominal aortic aneurysms. So comparatively, what happens today in the OR is when you have a endovascular aneurysm repair procedure or EVAR, what physicians will currently do is you have your aorta and there's ballooning in the aorta. What they'll do is they'll deploy a stent to reinstate regular blood flow into the aorta and essentially just redirect blood flow into this lumen, into the stent, and then back into um, the surrounding vessels. However, what ends up happening a lot of the times is that blood will go around the graft and kind of make its way back into the aneurysm, and that's what's referred to as an endoleak. There's also backflow of blood from these connecting vessels. So while this procedure is effective, it does have its downsides. So what we proposed is that we do a smart EVAR procedure where we use the Impede FX plug. Remember, that's the plug without the anchor coil. It's just the foam component with the marker band. And we use that to fill that aortic sac space so that after the stent has been deployed, physicians can deploy quite a few of our Impede FX plugs. And while as the plugs expand, that will form a stable clot. And this is initially motivated so that we can improve sac regression, meaning sac shrinkage, because what we want over time is the sac to actually shrink and the blood to just go through the stent. This is just some of the data that's motivating this work. Currently, what we have is 25% of EVAR procedures will result in expansion. So 25% of the patients who will come in, they'll get treatment, they'll get the stent deployed into their aorta, but over time they'll start seeing expansion of their aortic aneurysm. 35% are stable, and about 40% of the aneurysms actually regress, which is a pretty decent result. But we want to address this 25% of the market where, and also this 35% where people are still walking around with these large aneurysms in their aortic space. And this is a pretty dangerous thing to be walking around with, especially if it's expanding year after year, even after you've had a procedure done to treat it. So that's where we came in with this investigational feasibility study, which was the AAA SHAPE trial, where we used the rapid fill devices, which are just 5 of the Impede FX plugs loaded into an introducer cartridge, deployed into these aortic spaces. We had 2 centers in New Zealand and 3 centers in the Netherlands that agreed for us to do this work, up to 35 patients, and we followed them up to 3 years to see what their sac volume and diameter looked like at the 3-year mark, or whether they had expansion, regression, or stable aneurysm conversion. So just to quickly go over what the actual procedure was, once the physician has deployed this stent to kind of reinstate regular blood flow, they will then come in and fill up the rest of this aneurysm space quadrant by quadrant until the entire cavity is filled with shared memory polymer plugs. And on the bottom here is a depiction of our ImpedFX rapid fill device. This is five SMP plugs with marker bands that are loaded into an introducer cartridge that are then just deployed into that sac space. Again, this device is not approved by the FDA. It's still for investigational use because we are in the middle of a clinical trial. So the data that we saw at 3-year mark is that overall, we did see regression, and we saw more regression than what the typical outcomes are. So year one, we had about 58% of the patients that showed regress and 42% were stable. But then over time, that regress percentages started going up, but we also started noticing some growth. And that was just that could have been because the patients that were kind of getting this procedure done. There are other biological factors that were involved, such as age or diet. But what we did end up doing is we ended up moving that 40% regress percentage up to 58%. So we did improve patient outcomes at 3 years. And this is based on changes in diameter at least 5 millimeters. We also noticed a change in relative volume. So the volume of the sac also regressed over time in all of our patients, actually. So within our patient groups, we noticed that 76% of them had sac shrinkage at the 3-year mark. 15% were stable, and only 9% had growth, when in other procedures, we're noticing that 25% of the patients are seeing aneurysm sac growth. So overall, this was a very good mix of results that we get, and this is what motivated us to actually embark on our full clinical study that we're currently in the middle of. We have to enroll 180 patients for that, so a much larger patient group than this early feasibility study that we did. So now I'm going to shift gears a little bit and talk more about our core foam technology. Just some basic polyurethane principles. Most of you guys probably already know this. You have an isocyanate that reacts with a hydroxyl group, and that's what yields a urethane functionality. This is the basic principle that we're using in all of our film synthesis. The way the shape memory polymer specifically for us works is we're not just depending on the energy input or the heat input to cause shape change to occur. So typically with shape memory polymers, there's some kind of stimulus that causes the material to go from shape A to shape B. Our materials are thermally actuated, but we're also using to our advantage moisture plasticization. So what happens is once these devices are deployed in the body, you have elevated body temperature, but the dry TG of this foam is around like 54 degrees Celsius. So it's still way too high above the body temperature for any kind of shape change to occur. But what ends up happening is that moisture from that environment, from your aqueous body environment, will make its way and penetrate the polyurethane network that we have created, and it'll disrupt the hydrogen bonding between the polyurethane functionalities. And that is what drives the TG below body temperature. And once that TG gets down below body temperature, it's pretty easy to trigger actuation, because now a 37°C environment is actually elevated heat, and that's what causes the foam to expand. So we're using both the heat stimulus and moisture plasticization to cause our devices to expand. And we have the capabilities to custom engineer our foams to be susceptible to moisture plasticization. We're able to move the TG to very high, very low, sometimes even below 0°C. So these are all things that we can control in-house. Again, just kind of going through the basic principles of SMPs. We have our material that we have made in some configuration. In this case, it's this shape A. We will heat this component above its transition temperature and apply some kind of strain to crimp it from this open cylinder to a smaller rod geometry. This will cause the polymer chains to uncoil while the strain is being put on, and we will hold this strain onto the material and cool it back down below its transition temperature. And once we unload the strain, what we see is that the foam is in this metastable state where it is in a crimped rod geometry, but it doesn't necessarily want to be here from an entropic perspective. This is not the ideal entropic state for this material to be in, so it's just waiting for that external trigger to then go back and return to its original geometry. So when we reheat this material above its transition temperature, it'll re-expand back to its original shape, into its preferred entropic state. This process so that was specifically, we've just talked about shape memory polymers in general. I'm now going to talk a little bit more about how we specifically make our polyurethane foam. We're using a very common gas blowing method that's used in most of polyurethane foaming industry. We have a side A and side B resin that we mix. All the resins that we have, we make them in-house. We typically have a side A resin that consists of polyols. We have tetrafunctional and trifunctional polyols, which the resin will also include things like blowing agents that are water, surfactants for cell stability, and catalysts to expedite the reaction. Once we mix side A with side B tends to typically be our isocyanate resin. So we have some linear diisocyanates that we end up using. We'll combine these two resins using some high-speed mixing, and the resulting foam mixture will get transferred into a mold, which will then give us the foam that we then currently use in our devices. And over the years, what we have learned is we can tune our glass transition temperature, we can tune the hydrophobicity of the material by simply changing the ratios of the polyols and the polyisocyanates that we're using. So the gas blowing foam process occurs in several steps. After we have mixed our isocyanate and hydroxyl resins and some blowing agents, we see some initial bubble nucleation, and over time, and at this point, the material has pretty low modulus. It's not gelled at all. Over time, there's bubble growth, and we start to see the modulus rise a little bit. The catalyst will eventually kick in, while the blowing agents are also doing their job and causing more bubble expansion. So as the catalysts are kicking in, we start to see the modulus rise while there's more bubbles being formed. So the foam is actually rising at that point. Eventually, it'll get to a stable region where all of the polyurethane reactions have taken place. And as there's like gas escaping the pores, we start to see some cell opening. And then what we end up with is just a completely solid foam, a thermoset material in our case, that is stable at that point. Our foams specifically, we decided to use all aliphatic isocyanates and hydroxyls, and that's motivated by the medical application. We don't want to use any aromatics because that's where things tend to go wrong. That's typically what has gone wrong in the past when people have used aromatics in medical applications specific to polyurethanes. And then our material is amorphous and biocompatible per the various biocompatibility studies that we've done. Because we're using trifunctional and tetrafunctional polyols, we end up getting a very highly cross-linked network of polyurethanes, and this is a thermoset at this point. But the low molecular weight in between these cross-linked net points is what allows us to have this really fast shape recovery that we see in our devices. And so for the last couple of slides, I'm going to talk a bit about the biocompatibility, the degradation of our material. I mentioned our material is biodegradable, and we've done some work to assess in what mediums is this material biodegradable. So hydrolytically, our material is stable. We don't see any mass loss after 14 weeks in sodium hydroxide, though we did discover that this material is oxidatively degradable. And this work was done way before we were clinically approved, way before we did a lot of the animal work. So this was done in 2017. We were still kind of iterating on the device at that time. But we can see at 14 weeks and 3% hydrogen peroxide, the foam is starting to look like it's melting. So the strut integrity has gone away. The membranes are starting to disappear, and it's just not holding its shape like it should be. And what we found out further through additional academic research is that these tertiary amines in our trifunctional and tetrafunctional polyols are what were the points for degradation. So any area or any of these points that are circled in the green is where our degradation was taking place. Oxidatively, there was these linkages were getting broken, and then the degradation byproducts are just getting removed from the body through your urinary tract. These are just some animal studies we then did afterwards. On the top, we have a rat subcutaneous implant. You can see at day 0, the foam is maintaining good structural integrity. You can see the membranes, but at 12 weeks, it starts to look more skeletal. So something has been chewing away at the membranes, as we can tell from the SEM images. And what we learned from this is that our degradation mode is surface degradation. So macrophages or hydrogen peroxide is getting rid of the foam from the outside in rather than bulk degradation. And this was further, our degradation was further confirmed in a rabbit intramuscular implant, where on the bottom right, you see the foam that's kind of highlighted in purple. These black dots are the coil. So that's really not going to go away. But what we see at 26 weeks is that the foam has mostly gone away, and that aneurysm area where the foam was deployed has shrunk quite a bit. And we observed that at 180 days, there was complete mass loss. So that there really was like minimal foam, that you don't see a lot of the purpley foam that's available. And you can just see the regular tissue, the collagenous tissue around. So with that, I just want to end my talk and give thanks to our collaborators, specifically Lawrence Livermore National Lab, Texas A&M University, and we also had a lot of funding early on from NIH, which is what helped a lot of this research take place in a graduate environment. All the publications that we've had over the years, and we've now transitioned more from academic publications to more medical publications where doctors are talking about their patient outcomes using our devices rather than us publishing um, uh, papers about our foam component or our devices ourselves. So with that, thank you so much for your time, everyone, and I'll take any questions.
Wonderful job. Thank you, Dr. Hassan. Really, um, quite an interesting talk. Now, anyone who has any questions you'd like to ask will let you speak. Otherwise, I have some in the chat we can address. So anybody who'd like to speak up, feel free.
Yeah, first of all, this is Ajay Patsalgikar. Uh, First of all, I'd like to say a very nice talk, really helpful, and you did go into many of the basics. So I did ask some of the questions in the chat that Will probably will take up.
Yes, thank you. We'll go ahead and read one of your questions. It seems like one of your first ones was addressed during the talk, but I'll just mention it anyway. His first question was, can you comment on the shape memory effects and the TG of the polyurethane hard and soft box? I believe that came before the
Yeah, that's
slide regarding the water penetration. So
yeah. It
next,
was quite fascinating to see. The dual dependency of the plasticization and the temperature on the shape memory effects. So that was interesting to see.
Yeah, it's definitely a really cool feature to be able to harness because over the years we've treated water as a contaminant, but it helps us in the long term, especially once these devices are deployed, we can kind of bank on the TG getting quite low after the material is plasticized, and the shape memory effect can actually be a bit more enhanced after that.
the second question was, have there been any applications of your material in a non-foamed state, or does the shape memory effect occur only in the foamed state?
No, so we have had applications. Some of the early work for these SMPs was to create um, shape memory stents. So in the earlier research days, what they would do is cast neat films with these SMPs and then laser cut stents out of them. And that's what was initially motivating this work. But they found that a porous application worked a lot better for and the embolic space that they were trying to go into. That being said, we can definitely to this day still cast neat films and make different geometries out of our material. The inherent shape memory property of our material doesn't go away, whether it's foamed or in a solid state.
I was only thinking that in a foam state you will have a much greater effect of to the plasticization because of the
Oh, for
surface
sure.
area, as well as the biodegradation. So
Mhm.
you will degrade much quicker in a foam state. So that's why I was kind of wondering whether those effects are translated or maybe to a degree lesser in the non-foam state.
So because our material is surface degradation.
Yeah.
What we've seen, if we take like 1 gram of foam and 1 gram of neat film, it'll still degrade at the same rate because we are undergoing oxidative surface degradation. So it's just getting chewed up like a bar of soap. The porous nature of the foam definitely helps with moisture plasticization. So the more porous the material is, the faster it'll plasticize, which we don't really see with the neat films. It'll take a really long time for the water molecules to penetrate the neat film. But from a degradation perspective, they should both have the same rate of degradation because it's a surface degradation.
Okay, thanks.
I have a
Well,
question, Will.
yeah, go ahead, Len.
Hi, I'm sorry I missed the initial part of this. Got in late because of travel complications, but I did hear that you let it saturate with water after it's in place and then heat it. How did you heat it? Was it with the catheter core?
No, so our devices, once they're deployed in the body,
Mm-hmm.
they're still in a crimped state, and I can actually try to go back to let's see. Yeah, so what will happen is we will deploy a device that's in this crimped state into whatever vasculature that it needs to be.
Mm-hmm.
And while it's in the catheter, the foam is not really being exposed to a lot of water, and it's not being exposed to the higher body temperature. But once it's out of the catheter, what happens is water molecules will start penetrating the polyurethane network and start disrupting the hydrogen bonding, which will then drive down the glass transition temperature. And once that transition temperature goes down below body temperature, then the material sees the body temperature as the heat stimulus that it needs to expand. So we've actually done experiments where we have taken foam cylinders, crimped foam cylindrical rods, and dropped them in cold water. And they'll stay like that for hours, like nothing will happen. The material will get plasticized, but it needs that heat stimulus to expand. So once it's moisture plasticized and it's in an elevated 37°C temperature, that's what causes the material to open up and self-expand.
Okay, so it's body temperature. I thought I read 54°C. I
Yes,
wondered.
so that is that specific slide so this slide, under dry conditions, our glass transition temperature is 54°C. But once the material is plasticized with water, that transition temperature drops down to like 4°C.
I got
So
it.
when the material is at 4°C, 37°C is like a huge heat stimulus that will cause that foam to expand.
Terrific.
Mhm.
And while we're at it, let's take a break and open our adult beverages and get started with the happy hour.
Good thing.
Networking time.
Sounds good.
Working happy hour.
Cheers.
Cheers.
All right, I'll send it back
Cheers,
to you.
guys.
We'll go ahead with the Q&A.
Thank you, Len. I saw that Andre, you had a couple questions in the chat. Would you like to address those, or I can read them for you?
Yeah. So first off, thanks for the great talk. I love to see more biodegradable polyurethane work going on, and there are a few companies in different areas now that are starting to break through with biodegradable polyurethanes actually becoming commercial.
Mhm.
And So the first one I think you already got to about the what sort of biocompatibility. Well, you got to the degradation rate, but what sort of biocompatibility testing did you need to do initially before you even did those implant studies?
Yeah, so that's a great question. In an academic environment, we were mostly doing cytotoxic, like cell studies. So not really long-term biodegradation studies in animal models. It was close to, I would say, 2016, 2017, after we had evaluated cell cytotoxicity with our material, we felt confident that we should move into animal studies and like evaluate the degradation products there. We've also done, there's papers published on this. We've also done in vitro degradation studies where a graduate student took various foam samples and degraded them in potassium or in hydrogen peroxide over different time points. And he collected the degradation by, like, he basically took the degradation soup, neutralized the hydrogen peroxide, and evaluated what was in that media afterwards. And a lot of the byproducts that were identified were then evaluated by a toxicologist, and they were not something that is cytotoxic. We've also followed the full suite of ISO 10993 testing that you need to do from a FDA perspective, from a medical device perspective, and we've shown safety from a degradation perspective there as well. And these were a little bit more official long-term studies that we did in animal models to evaluate any adverse side effects in the animals themselves. But we weren't actively looking at the degradation byproducts in those animal studies because you just can't, because they're getting excreted. But we have looked at the specific composition of the byproducts in in vitro testing.
All right, thank you. I did have one more question. So when you are doing that mixing, waiting for the foam to rise with the aliphatics, it's generally, well, it's much slower than if you're using aromatics. So how long does it take you to get your foam to rise, and how do you like control that so that you have a good architecture by the time your foam is like fully reacted?
That's a great question. And this is not just me. This is years and years of research. There's so many other graduate students who came before me. And yeah, the issue is like aliphatics don't react as quickly. So we use catalysts for that specifically. And over the years, we have figured out exactly what concentration of catalyst we need to add, the concentration of surfactants we need to add to get this foam to rise quickly and be stable and not have a lot of artifacts like splitting and shrinking and all that other kind of stuff that you normally see when there is like a catalyst or surfactant imbalance. Our foam in manufacturing present day will rise within 2 minutes and it'll set within 2 minutes. So it's a pretty fast process for us.
Nice. And are you guys still, I don't know if you can say, are you manufacturing the foam yourself, or you have someone else doing it?
We're still making everything in-house. So yeah, our facility in San Jose is everything is kind of getting made in-house. We make the resins ourselves. We have chemists who actually will synthesize the foam. It's a batch process, but eventually we will move over to extrusion. And that's something that I'm excited. I'm looking forward to that.
Very cool. Thank you.
I have another one.
Go ahead.
Can I go ahead, Will?
Sure thing. Take it away.
The diagram or the cartoon that I saw with the stent in the shrunken and then in the expanded state makes it look like the cells are extremely large and the wall structure is tough. Is that representative of the size of the cells, or are they much, much, much smaller?
So this is definitely a cartoon, so it's like a lot bigger. This is not, our cells are not as big. The cells for our foam, I think they're mentioned in this image. This is really hard to read. We're at about 2 millimeters cell geometry. So each of
much
these,
smaller than the diagram.
yeah, much smaller than the diagram. So each of these cells, the pore size in the axial direction is about 2 millimeters. In the transverse direction, it's about 1.5 millimeters.
It's a reticulated foam.
Yes. So if you can see these like pinholes in the membranes.
We're not looking at any slides or anything.
Oh, are you guys not able to see my screen?
No, we're looking at you, your lovely image.
No,
Oh
I
no, I see the slide.
I think
Okay.
you might have to like move over to the different tab on
Okay, I'll
top
try.
bar of your Zoom.
Okay.
press view options.
It doesn't matter. Don't let me stop you. Please go on.
Yeah, so because over the years we've kind of tuned our surfactant concentration, we just get naturally reticulated foam where there are pinholes and disruptions in the membranes, so air can kind of go in and out of the foam. We also have a mechanical reticulation process in-house that again was designed by one of our engineers, and we do all that ourselves in-house where we will manually break apart these membranes. But from all of our studies over the years that we've seen is blood will find a way to get into the foam even with all the membranes and form a clot. So that really hasn't been a deterrent
Mm-hmm.
from a embolic perspective.
Good. Thank you.
You're welcome.
Great. I think we have one more question. It was about question about how when the polymer dissolves, what happens to the radiopaque markers anchor?
Oh, they just hang out. So that
Okay.
the radiopaque markers will be in the body permanently. We specifically use platinum iridium markers, and so they're completely inert. And what usually happens is during the wound healing response and the clotting cascade that's taking place, those marker bands will just get encapsulated by scar tissue. So your body will block that marker band off from any exposure to your vasculature.
Great. Thank you for all those questions, everybody. And thank you, Marziya Hasan, for your wonderful talk. I really enjoyed it.
Thank you, everyone, for having me. This was great. I really enjoyed it.